Hi guys, welcome back. I hope everything is going well for you and your families. I'm going to show you example number 2 from page 292, answering a little bit different questions perhaps. Part A, find the velocity and acceleration functions. So to find the velocity function, it is one derivative away from the position function. So we will just take the derivative of s, but with respect to time. And that is, take it down, multiply it around, it decreases by 1. Stop me if I make a mistake. Let's find the acceleration. The acceleration is one derivative away from the velocity, or it's two derivatives away from the position function. So taking the derivative of the derivative, we used to call it the concavity testing machine. Now we call it the acceleration. Take it down, multiply it around, it decreases by 1. Do it again, do it again, do it again now. Let's put these on a velocity testing number line. And when we do, let's find the critical values based on the first derivative test. Oh, before we do that, we have to answer the questions for part B. Part B, find the position, speed, velocity, and acceleration at t equals 2. So we need to find s of 2. We need to find v of 2. We need to find a of 2. And we need to find the speed. Speed's just the absolute value of velocity, so we should be in pretty good shape. Let me do the easiest one first. Shove 2 into the acceleration and get 24 minus 42. You guys can do those computations later. Let's shove 2 into the velocity generating machine, and we get you guys can do the computation later. And then the speed is just the absolute value of the velocity at 2. And the position function. I typed the position function into my graphing calculator because I need these values later when I draw my schematic drawing. So typing them in, going to the table at t equals 2, the position is 55. So there's one of our other values. Part C, at what point is the particle stopped? The particle is stopped when the velocity equals 0. So for part C, we're going to set the velocity equation equal to 0. I hope it makes sense that when the particle is stopped, the velocity should be 0. Factor out a 6. What times what's 10, but added together is -7. So it looks like this particle is stopped when t equals 5 and t equals 2. Coincidence. Let's put those on a velocity testing number line, 2 and 5. When we put 2 and 5 on the velocity testing number line, we can test the nature of the velocity leading up and on the other side of those points. Again, use the velocity testing machine when you're doing that. Since 0 wasn't critical based on the first derivative test, we can put a 0 in there and get a positive 60. So the velocity is positive. Roots of odd multiplicity will alternate on either side, and it looks like that. So at what points is a particle stopped? 5 and 2. These are both seconds. When is the particle speeding up and slowing down? That's what we need this velocity testing number line. And we also need the acceleration testing number line. So we'll make a number line, put it right beneath the velocity one. And it's used to be called the concavity testing number line. Now it's the acceleration number line. So set the acceleration equal to 0 and solve. Whatever 42 divided by 12 is. (42) divided by 12. How about 3.5? So we get a t-value of 3.5. Make sure you line it up as if it was on this first one-dimensional number line. 3.5 would be somewhere right in here. So we plot 3.5 on the acceleration testing number line. Let's find out the nature of the acceleration leading up to and on the other side of 3.5. Shove a 0 in and you get a negative and then a positive. So determine where the sucker is speeding up and slowing down. What I like to do is I like to riddle these zones with their values. That's my new one. That is a Western turtle. His name is Melman. Say hi to everybody, Melman. Hi to everybody, Melman. He likes to do calculus too. Remember, although 0 was not critical, it's important that we put a vertical line through 0 because that's where this experiment starts. In fact, somebody asked a question earlier this morning, do they all start at 0? The answer to that question is yes. These physics problems deal with the present tense, and so they all start at 0. Put a vertical line through all of these critical values so that we can determine where this sucker is speeding up and where it's slowing down. Remember, it's said to be speeding up when the velocity and acceleration have the same sign. So let's look for the intervals where they have the same sign. From 2.0 all the way up to 3.5, it's speeding up, and from 5 to positive infinity. Remember, for speeding up and slowing down, we're not going to include the endpoints. Where's this sucker slowing down? It's slowing down everywhere else, I suppose. When the velocity and the acceleration have opposite signs, from 3.5 to 5. So we covered the board. It's either speeding up or slowing down, or it's stopped. So, did you realize that all of the answers and their solutions are posted? I posted an electronic copy of both the textbook and the solutions manual for you guys. Next question, part E. Find the net and total distance traveled. So to find the net distance traveled from 0 to 5, all we have to do is figure out where this particle is at the end of the experiment and subtract where this particle was at the beginning of this experiment, and that's the net distance. Sometimes it makes a round trip. The total distance traveled is, we got to figure out how far we went left and figure out how far we went right. So we go right when the slope of the tangent line, or in this case, the velocity curve, is positive. So we want to find out how far we traveled in this zone. So that zone is s of 2 minus s of 0. On the other zone, where it's positive, is on the other side of 5. Well, we don't want that distance because we only want the total distance traveled from 0 to 5. So now we add that to the distance that we travel, but to the left. Distance traveling left is always going to be negative distance. So I threw that into the absolute value bars. It's S of 5 minus S of 2. Now, I hope that makes sense to everybody. In the next couple of days, we'll have a better technique to find the total distance traveled using the antiderivative. Okay, and then the moment that I've been waiting for, because I love doing these, is draw a schematic picture of the motion. So drawing a schematic picture of the motion, remember the number line is a position function number line. We want to highlight the position at all of these critical values, 0, 2, 3.5, and 5. That's why I put it into my calculator. So for this position function, let's find the values of S of, when I throw this in for t, 0, 2, 3.5, and 5. The position at each one of these points is on my table. So I just turned my graph on, hey girl, and the position at 0 is 3. The position at 2 is 55. Wow. At 3.5, 41.5. And at 5, 28. Gosh, that was a lot faster than doing it the old-fashioned way. So let's plot some points on this position curve. 0, 3. So I got 3, 55 is the biggest one. 3 is the smallest one. I'm going to put 3 way over here. I'm going to put 55 way over here. Then I'm going to put the other points in between. Halfway between approximately is 28. And a little bit further down the line, 41.5. At t equals 0, we start at 3. Again, by looking at the velocity, we start at 3, we go all the way down to 55, then we backtrack to 41.5, and then keep going all the way back to 28 before we change the direction after 5 seconds and head back this way. If we put them all on this one-dimensional number line, we wouldn't be able to see the overlappage in the distance traveled. So we hover up above and we plot our points. So we're going to the right for the first 2 seconds. Going to the right for the first 2 seconds, it looks like this. All the way up to 55. Whee! Then we change directions. Then we go to the left all the way up till t equals 5. And when t equals 5, we get all the way back down to 28. Whee! Pass right through one of the other critical values. And then we turn the direction. Whee! Anybody have any questions with that? If you do, email me. We're going to start checking in daily. Don't forget to check in with your attendance for sure. So we went this way. One barb for direction is all you need for each one of these changes of direction. Some people put a bunch of them on there. I just think it clutters it up. Next, we need to establish what the t values are at each one of these points. So t equals 0 over here. That's where t equals 2. And we skipped right through this guy. But at t equals 3.5, that's where it changes from speeding up to slowing down. And then back to this critical point at t equals 5. The only additional things that we need to do, hi Melman, how you doing? Is figure out where this thing is speeding up and where it's slowing down. Now Melman, he's a B-grade turtle. We rescued him. Get over here, buddy. He's a B-grade turtle. If you look at his back foot, he's got no toes. He was born that way with no toes. So he's a special little guy, and we're taking real good care of him and the others. So this sucker is slowing down on the interval from 0 to 2. So we put railroad tracks all the way. Does it make sense that it slows down before it comes to a complete stop? So we have to put our legend down here. It's slowing down. Looks like railroad tracks. And speeding up. Don't forget to put this on the quiz. And there we go. Then it's speeding up for this little stretch until you get to 3.5. When you get to 3.5 and beyond, that's where the signs for the velocity and acceleration are different, so it's slowing down. Then it stops and changes directions and goes the other way. That's all there is to it, guys. I hope you're doing well. Remember, talk to your parents about some of these problems and see if they remember how to do these problems, and keep up with a positive attitude. Keep up the good work. Talk to you soon.